Okay, so let's get started. We're working our way through the very last part of challenges in evolutionary robotics. We're going to finish lecture 21 today in our discussion of the Twitch Plays Robotics project. And then we will start into a two-lecture sequence on collective robotics where we're going to look at tasks that we would want robots to perform where it's difficult or impossible for one robot to perform it. So instead of having one complex robot, maybe we can have a group of robots to do so. But in order to do so, we're going to have to get them to coordinate in some way. And we'll look at evolving swarms so they evolve the ability to coordinate. And in lecture 23 next week, we'll look at an evolutionary add-on to coordination. So as your coordination strategies become more sophisticated, how do I communicate to you that I have a certain plan in mind, and for my plan to work, I need you to do X. For that, obviously, you need communication, and you need some form of language. Okay, so we'll get back to Twitch Plays Robotics in a moment. Any questions about the final project? You're working on weekly deliverable 3, which is due Monday night, where you are demonstrating to us that you've been able to implement the first of your milestones. As I mentioned before, for some of you this will be pretty straightforward if you're making a change to the body of the robot. That's obviously something that's easy to communicate in a screenshot. If you're making a change to the sensors or the joints or the fitness function or the evolutionary algorithm itself, those are all things that are invisible, right? So what we're looking for there is you thought cleverly about how to take that invisible change that you've implemented in your first milestone and you've made it visible in the screenshot, and that a student next year who tries to implement your project and implement your first milestone can look at the screenshot and say, okay, I can see now whether I've implemented this correctly or not. That's what we're looking for. Sound good? Okay, so back to Twitch Plays Robotics. So what we were walking through last time was a very recent project by Joey Netzberger, who took this class last year. This is an attempt to try and solve the symbol grounding problem. Who would like to attempt a summary of the symbol grounding problem? Exactly, right? So you're new to English, you ask me what the definition of a given English word is, I give you a dictionary and say, look it up. You look up that English word, and unfortunately the definition for that English word is defined by a bunch of other English words which you don't know, so you take that English word, go look it up somewhere else in the dictionary, and you never leave the dictionary, right? If you're a smart enough person or a smart enough computer program, you might learn all the relationships between every single word in the dictionary. But is that a sufficient understanding of the English language to use it, right? Maybe yes, maybe no. What we looked at last time is there's growing evidence coming from neuroscience and other sources that says that's not how we understand language. There's something else that's involved in our acquisition of language and understanding of language that's missing from a person or a thing that just tries to define symbols as relationships between other symbols. What is that extra thing that we seem to bring in when we're trying to acquire or understand language?
There's the physical world around us.
The physical world, and what is it about the physical world that we're bringing that helps us to ground symbols, or that seems to be helping us to ground symbols?
We assign symbols to, I guess, things that we see in the physical world.
Not just things that we see, right? Because we talked about deep belief networks last time, or any neural network that takes images as input, images of things that exist out there in the environment. We can learn to associate symbols with those pictures.
Like context.
Context, we're getting closer.
Like our kinetic feedback.
Our kinetic feedback, right? Our action. We push against the world, literally or figuratively, and we observe how the world pushes back. So it's not just the environment out there per se, it's our relationship with the world. And how do we understand our relationship with the world? We act, right? So it seems that there's a fundamental relationship between action and understanding words. And that's been hypothesized as a way that we ground symbols. Ultimately, certain symbols like jump or talk or pick or lick, these motoric words, they're grounded in action. When I say those motoric words, the motor strip in your brain is lighting up and you're at some level of consciousness simulating the action associated with the word jump, right? So those motoric words are grounded in action, and then more abstract words that are less motoric, like socialism, right? They are somehow related then to the symbols which are grounded. That's the idea. That's what has been hypothesized as a way to ground symbols. So what Joey investigated in the Twitch Plays Robotics project was, could we use that idea to allow robots to ground symbols in their actions, which generate relationships with the robot's environment? And the way that Joey has tried to do this, to teach robots to ground symbols in action, is to bring in the crowd and allow people to help robots ground symbols in actions, right? So that's why we're hoping that this is a scalable approach, because perhaps this project can be scaled up to more and more people teaching more and more robots more and more symbols. We'll see. We only have one robot and one symbol and 424 people so far, right? But it's a start. Okay, so that's a summary of the project. Again, we motivated this last time by looking at the Chinese room problem and the Turing test, where this symbol grounding problem came from in the first place. There are a lot of AI researchers who still believe that if we do give computers enough symbols and relationships between them, these computers will come to understand language. We'll see who wins. Deep belief networks, very powerful pattern recognizers. They do a great job of recognizing objects in images. Does a deep belief network understand a cylinder in the same way that we do if all it does is have access to images, but that this network has never physically reached out and manipulated a cylinder? Okay. Talked about the motor strip. We talked about this evidence that comes from neuroscience that says action seems intimately related with our understanding of words. When you mention motoric words, the motor strip lights up. We looked at linguistics, which is providing another line of evidence that action is an important aspect of language. We tend to think of language and mathematics as this high abstract thing that's very far from our basic interactions with the world. But as we looked at last time, if you look at metaphors, and a particularly abstract aspect of language, you can find that in most metaphors, there are motoric words that are hidden in there. On the quiz on Tuesday night, I was trying to find a metaphor that did not have a motoric word in it, and actually it took me a while to find one. I think there's probably more motoric metaphors than there are not, but there you go. Okay. We played around a little bit with trying to come up with as many as you could. Okay. So then I tried to create this cartoon for you to show how this idea might actually work. Again, this is just a hypothesis. We don't really know how humans ground symbols. This is one way to do it, by doing it in action. Okay, so then we switched to actually, towards the end of class, last time I was walking you through how the Twitch Plays Robotics project actually works, and I summarized it for you as 4 phases. First phase is the robot acts, and it acts randomly. I showed you that last time. We've got our little simple worm robot here, or our little legged robot. No evolution. It's just running random controllers, one after the other. And each controller is shown for about 30 seconds on the Twitch website. After the robot has acted, the robot observes how the crowd responds. And the crowd can respond, each individual of the crowd can respond with either this, positive reinforcement, or this, negative reinforcement. Positive reinforcement says, yes, robot, I think you were obeying the current command, whatever the current command is, and a thumbs down or a no says, no, robot, you are not obeying whatever the current command happens to be. Right? So we're collecting a whole bunch of these actions, commands, and reinforcement signals, positive or negative, from the crowd. We collect all of that information together, move on to phase 3, where now the robot is going to try and learn relationships between actions and reinforcement signals. So the idea is that at any given symbol, or in this project, any given command that has been issued by the crowd, we're going to consider that symbol to have been grounded if we can train a neural network that takes as input an action. So what did the robot do? And what we're going to feed as input is the sensory information that was produced by an action. Feed that into the neural network, and the neural network produces as output what? We ended with this last time. What is the output of the neural network? What is it learning to predict?
So if jump was, you fed it in the sensors that it had when it jumped.
When it was given the command jump.
When it was given the command jump, it then jumps. Like it produces the motors.
So remember that the controllers are all random, right? The controllers are random. They run on the robot. The robot produces touch sensor information. We take all that touch sensor information, feed it into another neural network.
Does it say whether or not the users are going to say yes or no?
That's it, exactly, right? So basically we have a neural network. We say, okay, neural network, the command was jump, and the robot did this, and we tell the neural network what the robot did by feeding in the touch sensor information that was generated when the robot acted. And there's a single output neuron on that neural network, and that single neuron is predicting whether the crowd on average did this, or if the crowd on average did this, right? So that's what we're trying to teach the neural network to do. The neural network is going to learn. So like some projects we've seen in the past, there's two different controllers here. There's one controller that is controlling the robot, and another, actually we shouldn't call it a controller, call it just a neural network. The second neural network is learning to predict whether the crowd will like or dislike a given action, given whatever the current command is. Make sense? Okay, let's go through that in a little more detail now. Okay, so we started with deployment, as I mentioned last time. So Joey had a robot simulator running on her local machine, and she was piping a live video feed to the Twitch website where millions of people go and watch people play video games. In our Twitch channel, people were watching a video feed of Joey's robot moving around randomly, and then the crowd was typing in whatever they were typing in response to, they were typing in their responses to what the robot was doing. We were collecting that all together into our database there. And then after this had run for 2.5 days, we had a data set, a hierarchically organized data set like this. So we had two robots, the worm robot and the legged robot, and every hour we switched the robot. For an hour, the crowd saw the worm. For the next hour, the crowd saw the quadruped. Next hour, the worm. Next, the quadruped. 1 hour after the other. Right? Within any given hour, at every 5-minute intervals, the command would change. And the crowd was allowed to issue whatever command they wanted. And if two people within that 5-minute period typed in jump, and a third person typed in forward, then at the next 5 minutes, the command that would be in charge would be jump. If while jump was the command during that 5 minutes, if the crowd, two people typed in forward and one person typed in jump, then forward would be the command that we were trying to teach the robot for the following 5 minutes. So every hour the robot changes, and every 5 minutes the command changes. During any given 5-minute period, there were a series of random controllers that were shown. So N stands for our controller, and a controller would be in control of the robot for 30 seconds. As the robot was being controlled by any given controller, in this case controller K, we collected the number of negative reinforcements we got back, so the number of no's that were typed in response to this controller, and we also collected the number of positive reinforcement signals we got for that controller. So far, so good? Right? Okay. So I walked you through this data set that we had before. We had 424 people participate, 57,000 controllers were sent. Some of them were not seen by anyone because it was 3 o'clock in the morning, there was no one on the site. But there were at least 6,388 controllers that were observed by people, and people typed in something in response to that controller. We got back over 16,000 chat entries from the crowd. We got, people voted for almost 9,000 commands. We had 266 distinct commands that were issued, and as we saw last time, the most popular one was jump, which was issued 385 times. And in response to these commands, we got back 7,500 yeses and nos, and the rest is statistics about, on average, how much individuals participated. And we saw the proportion of positive reinforcement, where O ranges between 0 and 1, and we got an average of 0.28, which is closer to 0 than it is to 1, which tells us that most people were saying no, but there was a little bit of positive reinforcement as well. Okay. We have all of our controllers here that we created. The controllers that the crowd responded to, so if we got at least one reinforcement signal back in response to a controller, we added it into this learning phase here, which we did after the whole experiment had finished, or the experiment on the web had finished. We replayed each one of those controllers on the robot and recorded the touch sensor information. So each part of the robot had a touch sensor inside of it. So now when we played back each of these controllers, we created an additional matrix that goes along with this controller. And that matrix records which touch sensor fired at what time. Right? So for the worm robot, which has 3 body parts and therefore 3 touch sensors, we have 3 columns corresponding to the 3 touch sensors, and every row corresponds to each time step during which that controller was executed. Right? We took our reinforcement signals and we computed our crowd response here, O, so we know how much or how little the crowd liked, or how much or how little the crowd thought the robot was obeying that command. And I showed you what this data looks like last time. Okay. And I think this is where we ended last time. So here's our neural network now, which is going to try and learn to ground the symbols. We took only those controllers that had been executed under the command jump. We wanted to first see if we could just ground one of the symbols. So not surprisingly, we took the symbol or the most popular symbol or the most popular command, which was jump. We took all of the controllers that were executed under the command jump. We took the T matrix associated with that command. We fed the top row of that T matrix into our neural network. We propagated it from the input neurons down to the output neuron. Then we took the second row in that T matrix, fed it as input, propagated it down to the output layer. And as we talked about on Tuesday, remember there's a recurrent connection here. So the recurrent connection allows this neural network to basically remember something about the touch information from the time step before. Right? So we're feeding all of the rows of this T matrix into this neural network. And as we do, the value at the output neuron is changing. And then when we finally get to the bottom row in this T matrix, we feed in that last row. We're done. We then look to see what is the number at that output neuron. and we treat that number as the prediction of the neural network about how the crowd responded. So in this cartoon example here, the neural network says, I think the crowd was split. It's close to 0.5. So half of the crowd thought the robot was obeying the command jump, and the other half of the crowd thought the robot was disobeying the command jump. O was actually, what does this say here? Oh, minus 0.8. I'm sorry, I forgot here that we're normalizing O. So a negative O means more of the crowd thought the robot was disobeying the command. A positive number means that the crowd is tending to think that the robot is obeying the command. We look at the difference between the actual response from the crowd and the predicted response from the crowd, and we take the difference between that, or the error, and we record that number. How far off was the neural network in its prediction? That's just one T-matrix from one controller. We had several thousand controllers that were executed under the command jump. So we take the second T-matrix now from that second controller, feed it through the same neural network. Now it makes a second prediction. We have our neural network. It took this action, this T-matrix, and says, I think the crowd responded in this way. Now it takes a second T-matrix and says, aha, for that action, I think the crowd responded in that way. Right? If we have, I can't remember how many we had. Let's say we had 6,000 of these T-matrices. From one neural network, we're going to get back 6,000 predictions. We know how the crowd actually responded to those 6,000 actions. So we take the average error in the prediction across all 6,000 actions. And that number is the average error, right? It tells us, on average, how well is this neural network doing at predicting the response of the crowd. So far, so good? Okay. You can imagine that when we start this learning process and we start with 4 random weights, how well does the neural network do in predicting the crowd? Not very well, right? Obviously. So what are we going to do? Now we're going to use an evolutionary algorithm. So far, no evolution. Now we're going to take these 4 weights, create a copy of those 4 weights, introduce a slight random mistake when we do, exactly like you did in assignment 1. Now we have a new neural network. Feed that new neural network all 6,000 T-matrices, one after the other, and compute the average error of that new neural network in predicting how the crowd responded to those six actions. So now we have 2 neural networks. We know the average error in those 2 neural networks. What do you think we do next? This should be sounding very familiar to you. What do we want this neural network to do? We want it to have a better average error, right? Or a lower average error. So let's say that this second neural network actually had higher average error than the first neural network. It's even worse at predicting than the original. Throw it away, go back to this one, make a randomly modified copy of this one. Now let's imagine that the new neural network has lower error than the original. Now which one do we throw away? This one, right? Rinse and repeat, exactly like you did in assignment 1. And if you do this for long enough, you get a neural network that on average does a pretty good job of predicting for any one of those 6,000 actions how much or how little the crowd thought that robot was obeying the command jump, right? Okay, so we get some neural network that has low error. Has this neural network grounded this symbol? How low does it have to be, right? This is kind of hard to say. How low before we would say, okay, this neural network understands what jump means?
I mean, ideally the error would be 0, but that's not likely to happen.
Possibly. We could, perhaps, maybe not with this simple neural network, but we could make a bigger neural network. And we probably could evolve it far enough so that it got an error of 0. But even thinking about that should be raising an alarm bell in your mind, given our discussion of neural networks. What's the problem? Overfitting, right? So perhaps this thing learns to predict all 6,000 actions perfectly, but it's possible that a neural network will overfit or it will memorize these 6,000 cases. Right? Remember I gave you the metaphor when we were talking about artificial neural networks. It's the night before a math exam, you haven't studied the whole semester. You memorize exams from previous years with the hope that you're going to get the same exam this year. If you do, you'll do okay, right? If the exam is different, you're not going to do so well, right? So even if a neural network gets 0 error on the actions that we have, we can't be confident that it has successfully grounded the symbol. So what should we do next to see whether it actually has learned, what jump really means from the point of view of the crowd? What would you do if you had a neural network that had very low error, and we want to know, does this neural network understand what jump means? Test it on new unseen data. And so that's exactly what we did. So we went from learning now to prediction, which is we took this set of 6,000 and we actually hid half of it. So we didn't actually train the neural network on 6,000. We took 3,000 at random. And again, I don't remember the exact number, but it was somewhere around there. We took 3,000. We trained the neural network on this for a couple hours. Then we took the best evolved neural network and we fed it the other 3,000 actions that the neural network had not seen before. That's what the question mark means here. And now we wanted to see how well it does on predicting the crowd response on that unseen data, right? So continuing the metaphor here, we gave the neural network a new exam that it had never seen before. And if it did well on the new exam, that's a pretty good indicator that it's figured out what in all of this touch information was the crowd originally responding to. Turns out that the neural networks that Joey trained actually did do a pretty good job in predicting the outcomes here. Given all I've told you about this project so far, what do you think it was that was in this matrix that allowed the neural network to predict the crowd's response pretty well? It wasn't perfect, as you can imagine. This is a crowd of people, but it did pretty well. What features of this matrix, which is just a binary matrix of touch information, either the touch sensor was firing or it wasn't, that allowed the neural network to predict that this matrix encoded a jump or it didn't encode a jump?
There's a time point where there were no touch sensors fired.
Could be, right? That would be my first guess, that there were certain rows in this matrix that were all zeros, right? All the body parts of the robot were off the ground, perhaps. I showed you some of the figures that Joey put together from last time. One of the things that Joey looked at was just what was the proportion of time on the ground, right? So how many rows had at least one in them, right? Because we could have also plotted proportion of time off the ground, which would have been the number of rows that were all zeros. Was it just the number of rows that were all zeros, or was it that there had to be a significant number of contiguous rows, one after the other? Did the robot have to be off the ground for long enough for the crowd to see it? You could imagine a robot that's kind of vibrating, moving around on the ground, where there are a lot of rows that are all zeros, but if it's just vibrating, would the crowd consider that a jump or not? Who knows? So that's what Joey is actually investigating now, is what did this neural network actually learn? Was it the number of all zero rows? Was it the number of zero rows in a row? Were there other things that the crowd was looking for?
Is it maybe a combination of all the whole matrix? So it's recognition pattern of the whole matrix?
That's a great question, right? Who knows? Probably not, right? Because even if the robot is on the ground and then suddenly does this, I would imagine most people on Twitch would say yes, there was a jump in there somewhere, but you don't need to look at the whole matrix for that. But another matrix, the robot might have stayed on the ground for quite a while and then jumped, right? So maybe the neural network does have to look at this whole matrix. There's no easy answer here, right? Because again, all you have is this touch information. What is it that the neural network is learning?
When you were giving it unseen data, the other 3,000,
Yes.
I'm confused. What are the 3,000? Are they new scenarios?
We have 6,000 controllers that the crowd saw, right? And the crowd, and someone in the crowd gave at least one thumbs up or at least one thumbs down. There might have been 5 people that responded to this controller. 3 thumbs up, 2 thumbs down. We have those 6,000 controllers. For each one of those 6,000, we also have a matrix that says which part of the robot's body was in contact with the ground at a given time step. That's what we have. And for each one of those 6,000, we also have this one number, which is how many positive and negatives. Make sense?
Yep.
Okay. So let's come back to the prediction part for a moment. Here's some results to actually show that the robots were doing well on the new exam. So what I'm plotting here is the average, or what Joey plotted here is the average error of these evolved neural networks after they had been evolved. And the green here corresponds to the controllers that I was just, the neural networks I was just telling you about. We looked at the controllers that were run on the simple robot and the complex robot. So the worm robot and the legged robot. So the crowd told the simple robot and the complex robot to jump quite a bit. So we actually did this whole process twice, once with the simple robot, once with the complex robot. And on average, the error is 0.42. So it was off, the neural networks were off by 42% in trying to predict the crowd. Okay, so is 42% good or bad? I don't know, hard to say. So what Joey did was to then look at 2 different controls, the red and the blue. The blue is pretty simple. The blue was, instead of taking an evolved neural network in the testing phase here, we just took a random neural network. So we set the 4 weights to random numbers between -1 and +1 and fed in those 3,000 unseen actions and looked at the predictions. And as you would imagine, the predictions are pretty poor, as you would expect. Okay, so that's kind of an unfair comparison, right? It's not that hard to do better than a random controller. Let's try instead to do a permuted control. So what is a permuted control? Permuted control is, we trained this neural network, like I explained before. We trained it on the 3,000 actions. Then we took the best evolved controller into the testing phase here. We fed in the 3,000 actions again, the 3,000 unseen actions. But now, here, the actual prediction, I'm sorry, I misspoke here. Let's go back to training here. We went through and we trained the neural network on 3,000 randomly chosen actions out of that total set of 6,000. But the O's that were associated with those 3,000 actions, we permuted those at random. So we took all of the actual 3,000 responses from the crowd and we mixed and matched them randomly. So there might have been action I over here, and there might have been unanimous thumbs up for this action. There might have been action J over here, and there was unanimous negative reinforcement for action J. We took that all thumbs up and then all thumbs down, and we swapped them. So from the point of view of this neural network, the crowd responded unanimously negatively to I and unanimously positively to J. But that was wrong because we randomly permuted the response. Right? The fact that this permuted control did worse than our actual experiment tells us that the crowd was behaving itself. Generally speaking, the crowd watched these 6,000 actions, and when the robot actually jumped, the crowd more or less said, thumbs up. And when the robot didn't jump, the crowd said thumbs down. The permuted control sort of says, what if the crowd was just randomly typing in Y and N at random? That's what the permuted control would have been, right? And it turns out that if the crowd had responded completely at random, this is the best that the neural networks could have done, because there's nothing there really to learn, right? The fact that the neural networks in the green case did better tells us that the crowd was giving us a good signal. There was some relationship between that T matrix and O, the crowd's response, and our relatively simple neural network could learn that relationship, or at least part of that relationship. Make sense? Okay, so again, as I mentioned, this is sort of brand new work. It's sort of a humble beginning. We have 2 robots, each of which have been able to ground, jump. Good start. Okay, where do we go from here? Well, let's have a look at the worm robot for a moment. And let's imagine for a moment, let's set aside the neural network that was learning the relationship between action and crowd response. Let's imagine that instead we've created a much simpler model, which is the linear regression model. So this dotted line here is the best we could do if we were trying to learn the relationship between the proportion of time the robot spent on the ground and how the crowd responded. Let's imagine now that the robot here is thinking about a new action to perform. And let's imagine that it wants to perform one action. It has one action in mind, and that action happens to cause the robot to spend 51% of the time on the ground. What is this robot thinking about how the crowd is going to respond? Can this robot be confident in how the crowd is going to respond? How specifically does the robot think the crowd is going to respond to this action? This robot is armed with this model here. It says, this is my best understanding of the relationship between action and crowd response.
It's going to have both positive, equal parts positive and negative responses.
Exactly, right? So the robot says, okay, I've got an action in mind. It causes me to spend 51% of the time on the ground. I think the crowd's going to be split. Either no one is going to say anything, I'm going to get back a 0, or one person is going to say yes, and one person is going to say no. 1 plus minus 1 is 0. Or 2 people are going to say yes, 2 people are going to say no. It doesn't know anything about how many people will respond, just that the crowd will be split, right? That's this point here. If you look carefully at the red line here, you'll notice that this red line does not intersect with any of the green points here. It's close to some of them, but the robot is considering a new action that it's never performed before and is trying to make a guess about how the crowd is going to respond. I don't know, is it going to be right? What about a robot that considers an action out here? It says, I'm considering an action where I spend about 95% of the time on the ground, this action around here. How does the robot think the crowd is going to respond in this case?
Most of the time it's going to be no.
The robot thinks that most of the time, let's go from this point here, we go up to here, it's actually guessing it's going to be more than unanimous, right? Everyone is going to say thumbs down. So now we are armed with a robot, even in this simple case, where the robot is able, before it performs an action, to think about how the crowd is going to respond to that action. That alone is a pretty interesting idea, right? This is a pretty important thing for robotics. If we want to have robots that operate in the everyday world with us, we would like those robots to be able to think about what is going to be the social repercussion of any action that I perform. Imagine a robot that's working alongside some humans and it knows that there's a human very, very close to it, and the robot is considering extending its arm at maximum velocity. you would hope that that robot has some understanding of people to know that that is probably something that the person standing right next to me is going to respond to negatively or is not going to like that action. Okay, the reason I bring that up is I wanted to spend just a couple of minutes talking about the ethics of robotics. I've deliberately avoided this subject throughout the course so far. As I mentioned at the beginning of the class, we could have a whole class on the ethics of robotics. It is a question that is very much in vogue at the moment, so I thought we'd spend a couple minutes talking about this. So it's completely optional. I am not an expert in ethics, so let's think about this together. If you haven't read this book and you're interested in AI, I highly recommend it. Nick Bostrom is a philosopher at Oxford, wrote this provocative book on superintelligence, where he said, all right, let's leave it to the nerds to figure out how to make a superintelligent machine. Now that we have, let the philosophers take over, and we'll tell you about what we think is going to happen, assuming that does happen. So again, take this with a grain of salt. But it's an interesting book because he sort of sketches out all the possible paths that might happen. One of the most common paths, or one of the things that seems very likely with any superintelligent machine, let alone a superintelligent machine, any autonomous machine, is the problem of perverse instantiation. I called it pathological here. I think Bostrom refers to it as perverse instantiation. What is perverse instantiation? Well, let's imagine, I'll follow Nick's example here. Imagine we do achieve superintelligent AI, and we give the superintelligent AI the following utility function: make most people in society happy. You're the superintelligent one, you figure out how to do it, but that's your fitness function. Make as many people happy as possible. Turns out, even if you're not super intelligent, you can quickly think of a pretty simple solution to this. The super intelligent AIs surgically implant a wire in everybody's brain into the pleasure center of your brain, and you just supply maximal current to that wire. Everybody is very happy, right? You have a super intelligent machine that has maximized the utility function that you gave it, make everyone happy. Probably not in the way that you would like to be made happy. It's not the way I would like to be made happy, right? So, okay, forget that plan. Let's go back and revise our utility function. Make most people in society happy without any surgical procedures. How does that sound, right? That sounds safe. Let's give that utility function to the super intelligent machines. Try your best to think like a super intelligent machine for a moment.
Well, everyone doesn't specify a specific number, so if everyone but a couple very happy people are dead.
There you go, right? So how many people maybe we should make 70% of the people really, really happy and the other 30% maximally unhappy. That's better than everyone at 50%, right? If you do the math, that sum adds up to a higher value of that utility function without surgical procedures, right? The difficult thing about perverse instantiation is you can usually always imagine, if you sit down and think about it, you can come up with a perverse way of maximizing that utility function, despite however many constraints you put in. Remember our discussion about the evolution of passive dynamic walking? I want the robot to displace, but I don't want it to displace in this way, and I don't want it to displace in that way, and, right? We can keep adding on these constraints, but a super intelligent machine can probably always find a way of maximizing that utility function in a way that we probably wouldn't like in retrospect after the machines have implemented them, right? Again, yes, that may be a problem for super intelligent machines, but this issue of perverse instantiation is going to be a problem in autonomous robotics much sooner than that. So back to the evil starfish for a moment. I usually show this as an example of perverse instantiation. We ask the robot to get from the left side of the table to the right side of the table. We build it as a quadruped, expecting the robot to stand up and exhibit one of the quadrupeds. It maximizes the utility function of the fitness function. From the left side of the table to the right side of the table, but definitely not in the way we were expecting it to do it, right? This was quite surprising. Surprising, not dangerous in this case, because the robot wasn't interacting with anyone, but it's important, right? It shows that, or at least as a roboticist, my experience has been that perverse instantiation is pretty ubiquitous. You probably started to see this already in your 10th or your 11th assignment, right? You're probably evolving robots now that maximize your fitness function, but not in ways that you were expecting it to do it, right? So this perverse instantiation issue, let's set aside superintelligent machines for a moment, is a real issue as we move forward into autonomous robotics. People have thought a little bit about this. There's, again, some interesting philosophical discussion around this. Yudkowsky in 2004 wrote this interesting white paper with the mouthful title here of Coherent Extrapolated Volition. Yudkowsky is a member of the Singularity Institute, so you can take his views with a grain of salt if you like. But it was an interesting approach to solving or dealing with the perverse instantiation problem. Yudkowsky said, in order to make an AI friendly, friendly AI should only implement policies in a way that, despite our differences, our future selves would be likely to approve of these policies in retrospect. So let's deal with the last one first, volition. So our future selves would think it was a good idea, right? If a machine manages to hold you down and put a wire into your brain and maximize the pleasure center of your brain, you would probably thank it for doing it. Your present self would thank you for that procedure, right? But your future self, looking back on it, having either had the surgery reversed or having been told, your future self having been told 20 years ago machines were considering doing this, you would probably thank the machines or the people that stopped that policy from being implemented, right? Bostrom talks about this example in his book. Imagine an alcoholic. An alcoholic might thank you for giving him or her a drink in the moment, but many years later, after dealing with alcoholism, may thank you in the future for retroactively not have given you a drink in the moment, right? So this is extrapolated volition, right? A machine should be thinking about different policies that will make members of society happy, and thinking about will future humans retroactively look back and thank the machines for doing so. A tricky thing to do. The coherent part here, this is probably the most controversial part of this theory. The coherent idea here is despite our differences, that we will cohere in the future. We will be more ideologically aligned in the future. So despite our differences, in retrospect, looking back, we will be more unanimous in thanking a machine or cursing a machine for implementing a given policy. Again, you can take that with a grain of salt. Okay. There's other challenges with this idea of coherent extrapolated volition. The biggest one, of course, is it requires an accurate model of future human behavior.
So, like, our not wanting a wire in our head that makes us happy, right? Like, we can't really pin down why that doesn't seem tasteful, but it's not.
It may not matter whether we can pin it down or not.
Right. But what I'm saying is, you could argue that the reason it's not tasteful is because we've been, socialized a certain way, and we have these taboos in our lives, and et cetera, et cetera. So, like, wouldn't the only way to make a machine that's understands what is tasteful and not tasteful to be to try and socialize it the same way a human being would be socialized?
Perhaps, right. You want to try and have a machine that shares our values.
Yeah, like if we don't, if we're going to be operating under the modernist, everything's relative, etc., then the only bedrock we have is the weird hodgepodge of rules that we've got. So if we don't teach it to those hodgepodge of rules, then I don't know if we could even call this perverse in a sense of it negative connotation. It's perverse in that it's not following our set.
Right.
But
what we would like and what we would not like, regardless of why, right? So the question is, should the machine share the same values as us or share the same values as our future selves would? The idea here is maybe not. The machine itself doesn't need to know the machine itself does not need to share our values as long as it understands our values and can predict our responses to policies based on its understanding of our values, right? So if a machine has an accurate model of human behavior, the machine can say, I'm considering policy A and policy B. I wonder how people will respond to A and how they will respond to B, right? In order to carry this out, it has to have a model of human behavior, not necessarily share the same values we do. I wouldn't know how to build a machine that has human values. I have a better idea, at least, of how to go about trying to build a machine that builds up a model of human behavior. We just saw an example, right? Again, a very, very humble example. But in Joey's project, that machine, which was just a simple neural network, has some understanding of how the crowd will respond to different kinds of actions, right? Could that approach be scaled up and generalized and abstractified to be able to make predictions about human response to things other than just jumping up and down or moving forward or back? Who knows, but an interesting thing to think about. Okay. The superintelligent AI could probably think up some policy that implemented now will cause future selves to look back and thank the machine for doing so. But again, that's kind of cheating, right? You don't want to have the machine influencing our future selves to solve CEV because now you're back to perverse instantiation. What you would like the machine to do is to be able to think up a policy and know that that policy would be a bad idea. So the machine should say, I know that if I do not implement policy B, future humans will thank me for not implementing policy B. If it can make accurate predictions along those lines, along with other ones that say, I'm pretty sure that future humans will reward me for implementing policy A, then we're in good shape. Right? We're getting closer to a friendly AI. Okay. Right, would signal remorse that a given policy was not implemented now. Okay, again, this is a little philosophizing for you, little thoughts about ethical machines. The point I want you to take away from these couple of slides is generally, if we want to try and make machines that are both autonomous and safe, it's hard to imagine a machine that could be both autonomous and safe without having a good model of human behavior. If a machine does not have a good model of human behavior, how can it know that anything it decides to do autonomously is going to be a good thing or a bad thing from the point of view of the humans that are going to be affected by that policy? So somehow we're going to have to figure out how to create machines that are autonomous and also able to build up a better understanding of how people would respond, to policies that the machine or the robot has never tried out on humans before, right? This is sort of the million-dollar question. Okay, a little bit of ethics, first thing in the morning. Any questions about that before we move on to swarm robotics? Actually, this worked out well that we talked about ethics before we get into swarm robotics, right? Okay. Okay. All right, so as I mentioned, we're now going to discuss collectives of robots. In lecture 22, we're going to focus on coordination, so robots working well together. Lecture 23, we're going to focus on communication, where communication presumably evolved as a way to help humans or animals coordinate together better. So coordination, then communication. Okay, so swarm robotics, of course, we have biological swarms already. We have all sorts of different forms. I'm going to have to find this video. Bear with me a moment. Any ornithologists here? Anybody know what this bird species is? So these are starlings, one of nature's best swarmers. Which bird is in charge? Which bird is deciding which way the flock goes next? Whichever one's in front, maybe. None of them and all of them, right? That's the answer. Okay, if all of them are in charge, right, we tend to be a very hierarchical species. This is kind of hard for us to wrap our minds around, right? How can this swarm actually move in this beautiful coordinated manner without any two birds bumping into each other when no one is in charge? How does this actually work? Again, no one is actually sure, but we're starting to get an idea. Starlings aren't the only animals that perform collective action. You get schools of fish as well. Why do some species of fish school? What's the adaptive advantage of this? Why do this? Protects them from a predator, right? If you're whatever fish this is here, you step outside this group, you're in trouble, right? So very good evolutionary reasons for flocking or herding or schooling. How is this actually done? Of course, if you have a large enough group, no one animal can be in charge, right? If we would like to build robots that also perform collective action, and we have enough of them, and we also cannot have any one of them be in charge, how are we actually going to do this? People have been trying to do this actually since the 1980s. So Craig Reynolds, who worked in computer graphics, designed boids back in the 1980s. Here's a cartoon of these boids over here. Every single boid in a boid swarm is running exactly the same program. So they all have exactly the same program. But each boid in the swarm performs slightly differently because the local context of each boid is slightly different. How does that work? Well, let's consider the green boid here for a moment. Every boid has a limited range that it can sense, which is represented by the large circle here. So this green boid here can only see neighboring boids that are within the sphere of its sensory radius. The boid can detect its neighbors in that sphere. It can detect the position of those neighbors relative to itself. And it can also detect the heading of its neighbors. That's what the little line here represents. So if we want the boids to move together, you can actually do it with just a few lines of code where you create 3 separate procedures here. And the new position and heading of the green boid is by summing together the results of these 3 procedures. So let's start with separation. This boid looks at all of the other, it looks towards all of its flock mates inside this sphere, and it looks at its relative distance from all of them. It sums the relative distance, and if there are more of its neighbors, whichever side there are more neighbors on, in this case left, then at the next time step, the separation function is going to turn the heading a little bit to the right. So separation is steer away from your local flock mates. If you have a bunch of neighbors and they're all equally spaced around you, then just keep going straight. But if you're crowded on any one side, turn a little bit away from that side.
What causes the swarm not to explode outward then?
Very good question, right? So if everyone was just running, if every boid in the swarm was only running separation, and you put them all together and turned on the simulation, they would all move away from one another, right? And the moment that, as a boid, I no longer see any other boids in my sensory radius, I just keep going straight, right? So with just separation, the swarm would very quickly cease to exist. So we're going to counterbalance separation with alignment and cohesion. Let's do cohesion, which is the inverse of separation. Again, look at the position of all of your neighbors. Compute the average position of your flock mates. So take the positions of all of these guys, find the average position, and then now turn towards that center. So if there's too many of your neighbors that are too close, turn away. But if they're not too close, if they're kind of generally far away, so the influence of your neighbors is relatively less, then move towards them. So if you're crowded too much, turn away. If you have room to breathe, look at all of your neighbors and turn towards the average position of your neighbors. Alignment, look at the headings of all of your neighbors, compute the average heading, which is represented by this blue line here, and alter your heading a little bit to more closely align with the average heading of your local flock mates. Okay, so at every time step of a simulation of a boid swarm, every member of the swarm computes these three functions, and each of these three functions outputs a delta, which is the desired change in heading that those three procedures want. Take those three deltas, take those three desired heading alterations, sum them together and divide by 3. Take the average, which will give you what the new heading of that boid should be at the next time step. Do that for all the boids in the swarm. Now you have a new heading and a new position of the boids at the next time step. Do it again and again and again. And if you do, you get this. I apologize for the quality of these videos. They're relatively old. Okay, so you not only get swarming, but you also get other nice behaviors like effortlessly flowing around an obstacle, which breaks the swarm into two, and then it reforms on the far side. How is that possible? There's nothing in these three functions that says anything about look for obstacles and avoid them and reform on the far side. How does that behavior emerge from these three simple rules?
The obstacle gets in the way, they lose sight of the ones that are going on one direction.
Absolutely.
They stick with the partners that go with them around it.
Exactly, right? There's the swarm and it's approaching an obstacle, and just because through the collective action, now I can sort of only see some of my neighbors that are more on the right, and they're a little bit further away, so cohesion gets me to turn a little bit towards them. I might also be crowded by the obstacle which is approaching me front left. So I'm also separating or avoiding the obstacle and being pulled towards my mates. But the ones that are at the right-hand edge of the swarm, right, they have no neighbors to their right. So cohesion is getting them to track and stay with their neighbors who are staying with the obstacle, right? So no one flies off in a random direction. And when you get to the far side of the obstacle, suddenly those in the right-hand swarm see their neighbors on their left again and get pulled towards them, and vice versa, and the swarm reforms on the far side. So this is one of the amazing things about this very simple algorithm, which was formulated in the 1980s in computer graphics, is you can get lots of other interesting and natural-looking behaviors. In the interest of time, I won't play this video, but this became and is now a standard toolkit in the animator's toolbox.
So the previous video is the representation of the algorithm?
It is a simulation of little agents, and each agent is running those three programs one after the other.
So is it those three that dictate like where in the simulation that it goes? Or how how do they essentially know to move forward in addition to?
Right. So I forgot to mention that. Let's just assume they all have constant velocity. And the only thing that the green boid here is figuring out is new desired heading. So imagine that its heading is true north for the moment. The individual boid computes separation, alignment, and cohesion, combines the three numbers that come out of those three functions, and the sum of those is plus 5 degrees. So that's what that's saying is the boid says the next time step, I'm not going to point at true north, I'm going to point 5 degrees clockwise from true north. And now the simulation updates the new position of the boid according to that heading. So now that boid has a new position and a new heading, and you compute the whole thing again and again and again and again.
So is that like what generates the almost random kind of flow around the?
Exactly, but it's not random, right? That's the whole point. Is the velocity is fixed. They're all just moving, but where they move is dictated by their heading, right? So if this guy is here and its heading is here, he's going to end up here at the next time step. If this guy's heading is this, at the next time step, this guy's going to end up here. Make sense?
Yeah.
Okay, so the boids was first used in the Lion King movie. If you go and find this clip on YouTube, you see these wildebeest that run through the valley, and they don't bump into each other, and they avoid the walls of the box canyon, and they flow around spurs of rock and so on. Right? It was a shocking animation back in whenever the Lion King came out, and again, this is something you see in most modern animation movies, where you can now program, quote unquote, you can program indirectly coordinated action of very large groups of animated individuals without having to manually decide what is the new position of every agent at every time step. Right? So with relatively simple rules, and again with no one individual in charge, you get coordinated action. Right? No boid here is saying, follow me, I know which way to go around the obstacle. Right? They are each making local decisions about their new heading based on their local information. What are my neighbors doing? That's it. There's no global information. There's no global leader. Everyone and no one is in charge here.
Does anyone see the column at all? Ever?
They
Like
do see the
first-
column.
Okay.
Yes, so from the point of view of the boids, it's just another boid. There's something on my left.
I see,
Right?
so it does also
Right.
react to objects. So the first guys are seeing it. and
Yes. They do see it. Right.
Using, what is it, separation.
Using separation, exactly. That's right. There is something crowding me on my right, and it's crowding me more on my right because I'm moving towards it. So the closer I get, the more I steer away from it. Yeah, exactly. Okay, so why are we talking about swarms? Why are we talking about swarms at all? Well, as I mentioned again, there are obviously things that are beyond any one human or animal or robot. So let's take an example from nature, group hunting here. This is a velocity curve for a lion and Thompson's gazelle. This is taken from the Principles of Animal Locomotion book, which I passed around when we were talking about legged locomotion. Okay, if you were a lion and you were trying to get your supper, what would you do? One lion, one gazelle. You're the lion. Absolutely, right? If you don't catch the gazelle within 4 seconds, you're never going to catch the gazelle. If you have cats at home, there's a reason why they lay low and move very, very slowly and only then accelerate. If you are a cat, big or small, best thing you can do is get as close as you can to your prey and then accelerate as quickly as you can. And if you haven't caught your prey in 2 seconds, don't bother, right? Or 4 seconds, don't bother. Okay, so an obvious example, but there's an infinite number of them in nature, right? There's certain things that are beyond any one individual. So some lions do this, but some other lions formulate a different strategy, which is Go find your lion buddies and figure out how to coordinate your action so that you have a chance of catching the gazelle, even if the gazelle knows you're onto them, right? You might have more than 4 seconds. Okay, so the reading for today is looking at group hunting robots. So good thing we just had our ethical discussion about safe machines, because now we're going to talk about pretty aggressive machines, right? We're going to look at this domain. So actually we're going to look at virtual lions and virtual gazelles. The reading is a relatively old paper in the field, but is a beautiful example of how you can actually evolve these coordination strategies. If you are one lion and you have 3 lion buddies, and the 4 of you are trying to coordinate your action to bring down a gazelle, how should you do it? What coordination strategy is the right one? Okay, so in this paper, Luke and Spector tackled 3 different questions. Can we evolve behaviors for a team of predator? How would you actually set up the evolutionary algorithm? What would be the fitness function? How would you simulate the lions and gazelles? And then, assuming that you can, will they actually evolve a coordination strategy? And if they do, what will that coordination strategy look like? Okay, so let's put on our pith helmets and go out onto the virtual Serengeti here and observe some lions and gazelles interacting. This is the virtual Serengeti here. So this is, again, early 1990s, no physics engines. This is a very simple 2-dimensional plane. They simulated the lions and gazelles as simple agents, and those agents simply had a position in the 2-dimensional plane. They simulated 4 lions, L1 through L4, and a single gazelle. The gazelle, as you can see, moves faster than the lion. So at every time step of the simulation, the gazelle can move 3 units of distance. And at any one time step, the lions can only move 1 unit of distance. So this is actually even worse than real lions and gazelles, or at least worse for the lions. The lions are 3 times slower than the gazelles. Luke and Spector pre-programmed the behavior of the gazelle, but they evolved the behavior of the lion. So this is not evolving the strategies of both. They fixed the prey behavior, and they're going to evolve the predator behavior. The gazelle's behavior is fixed, and as you can imagine, is pretty simple. The gazelle is going to look and see where the lions are and sum those 4 vectors that connect the lion to the gazelle. It's going to sum those 4 vectors and then move in the opposite direction, and we're going to evolve the behaviors for the lions. Okay. This virtual savanna, if you like, is toroidal, which means basically it's infinite. So let's see. So here's our virtual Serengeti here, our virtual savanna. If you take the 2 long edges and connect them, and then you turn this and connected the 2 circles, you'd have a donut, which is the toroid. So basically, if you have the gazelles and lions that are moving across the surface of this toroid, you can simulate in this in 2D that if a lion or a gazelle ever moves beyond this savanna, then they magically wrap around to the far side. Right? So in these visualizations, you're looking at a finite plane, but just keep in mind that it's infinite. Okay. So the solid arrows here represent movement, and the dotted lines represent sensing. So the lion is always looking at the gazelle, and in this picture here, imagine that the gazelle is here at time t, and at time t plus 1, it moves here. If lion 4 is sitting here, lion 4 is not looking here, it's looking here. Right? So L4 is actually quite close to the gazelle. Just to keep that in mind. Okay. So again, I mentioned what the gazelle is doing. The gazelle computes the 4 vectors that connect it to the 4 lions. We then sum those 4 vectors. So uppercase V over here is a set of 4 vectors that connect each of the 4 lions to the gazelle. We're going to sum those vectors. We're also going to compute the length of the maximum vector. So how far away can the gazelle ever be from a lion? The answer is if the gazelle is here and a lion is here, that is the longest distance that a gazelle can ever be away from the lion. And we're going to use that to normalize this sum. So we're going to draw out one after the other each of the 4 vectors in the set of 4 vectors. We're going to take that vector, we're going to sum the 4 vectors together. We're going to divide, first of all, by the length of each of these 4 vectors. Why are we dividing each vector by, why are we changing the magnitude of this vector according to the inverse of the length of the vector? So the gazelle is looking at the 4 lions. It has these 4 vectors, v1, v2, v3, and v4. It's going to sum them together, but it's not a straight sum, it's a weighted sum. Why a weighted sum?
It wants to run as far away from the nearest lions as possible.
Absolutely, right? So the closer a lion is, the smaller the length of v is. So by dividing by that small length, you exaggerate the influence of that vector on the gazelle. In essence, it's going to pay more attention to the lion that's closer, which makes good sense, right? And then we just normalize this by the total. Then we negate the final summed vector. Why negate it? Sorry? Go in the opposite direction, right? If you don't negate it, you're going to compute and run towards the closest lion, right? So minus sign says run in the opposite direction. Okay, I think we will stop there for today. You have a quiz due tonight, and weekly report number 3 is due Monday night. Thank you very much.